Welcome everyone, wherever you are in the world, and thank you for joining us today. I'm Brenda Dettinger from BIOPAC, and I will be your moderator on today's webinar about remote eye tracking and the advanced integration with physiology data that BIOPAC now offers. Today, we're going to explain how to create an eye tracking experiment that combines the physiology data with remote screen-based eye tracking. We have two wonderful speakers and a comprehensive demonstration. It's going to be a very good webinar. First, I have some housekeeping. All attendees are muted to keep our lines clear, so please submit your questions through the GoToWebinar control panel on the right of your screen. You can just slide that control panel in and out. We do have a full agenda, but we plan to take questions live throughout the webinar and at the end of the webinar. And today's webinar is being recorded. We'll send each of you a link out to the recording tomorrow. Now on to our presenters. I'm excited to introduce our experts today. We have Frazer Findlay, the CEO of BIOPAC. He has over 20 years of experience in the life sciences and physiology monitoring industry. Welcome, Frazer.
Good morning, Brenda. Good morning, everybody.
And we also have Keith Jackson from EyeTech. Keith has over 15 years of experience in the eye tracking industry and will tell us about the eye tracking bars and remote screen-based eye tracking. Welcome, Keith.
Thank you, Brenda. Good morning, everyone.
All right, Keith, let's start with you. I'm making you the presenter. Are you ready?
I am. Okay. So we're going to go over eye tracking fundamentals today, and later on, Frazer will do a deeper dive live demo of the AcqKnowledge integration with our eye trackers. We're really pleased to have partnered with the BIOPAC team to integrate with our API into their great platform. Just wanted to give a quick summary of our company for those of you new to EyeTech. We are based in Phoenix, Arizona. We've been at eye tracking, one of the pioneers. Been doing this since 1996. We have over 10,000 users around the world in 35 countries, and we do sell B2B through value-added partners like BIOPAC and others. We are focused on our core product, which is our eye tracking on a chip technology that we launched several years ago. It leverages the Xilinx Zinc FPGA. It's a great platform that gives fixed hardware timestamp data, so you get very reliable results every time, regardless of whatever computer you're using. You get the same data quality because it's all done on the chip. We can adapt to multiple operating systems. We currently support Windows and Android, and this technology is currently in our VT3 module, which can easily magnetically connect to any screen through a single USB connection, and it can run up to 200 frames per second. And it can support screen sizes when it's physically attached to the screen of 24 inches or smaller. But we do also have a convenient desk stand, so you can use it on larger screens as well. You just place it a few inches or feet away from large TV screens as well. And we're pleased to actually have announced earlier this year at the Consumer Electronics Show, we did a launch of our new Ion device, which is the first thin, lightweight, all-in-one eye tracking tablet on the market. This leverages our new AI 2.0 technology, which is our second generation eye tracking on a chip technology, same fixed hardware timestamp data quality, but with a higher resolution camera, 8 megapixels to be exact, and then the camera can go up to 500 frames per second for really high-end medical research grade eye tracking. You'll see this rolling out into more clinics and medical applications with some of our commercial partners as well. Has built-in VESA mounting and integrated stand. So it's a really nice 14-inch screen size, running Windows 10 Pro, really responsive i5 Intel Core i5 processor, and it also has a convenient HDMI port on the side that you see here, so you can have a second screen or display to like a larger monitor when you're doing presentations, things like that. It also has 2 USB ports on the side and is a nice thin, only 18 millimeters thick, all-in-one tablet design. It also has a front-facing webcam, so you can get a motion tracking, and then also a rear camera on the back of the tablet, so you can leverage that for your application and research for more AR applications. We do also have an excellent quick link to API, so you can stream the data into your own program, such as XY gaze data, fixation, saccades, microsaccades, pupil size, and then we have wrapper support, including C++, C#, MATLAB, and Python, to name a few. We do have full integration with AcqKnowledge, thanks to Frazer and his dedicated team, so you can synchronize all the data streams into one software, which will greatly reduce the amount of time it takes to do your research with ECG, EKG, EMG, and eye tracking and other physiological sensors. Just to give you a quick demo of how we quantify our accuracy and precision, our robustness scores, we have a tool called Quick Test, which I'll show you a live demo of how we do what we do. This is how we run hundreds of participants through to quantify when we update our eye tracking on a chip technology from one camera firmware to the next. We can quantify that we are more accurate, more precise, more robust in a battery of tests that we run subjects through. So you can see we use a dark pupil technique. Down here at the bottom, you can see we output the distance in real time, and it has a nice, comfortable head box, large head box both forward and back and side to side. And let me just show you a live demo of a simple calibration. I'm just going to follow the moving target. And in about 5 seconds, you can see the right and left eye accuracy on each of those 5 points is very accurate. We'll go ahead and accept that, and I'll show you one of a battery of tests that we use to not only compare our camera firmware from one to the next, but also to compare against our competitors, so you can have best-in-class accuracy and performance. So you can see my live gaze is the green dot. I'm looking at the white dot, and it continues to get smaller and smaller after I look, and I'm able to look at the target. You can see we're getting almost pixel perfect accuracy with our eye tracker. You'll notice that there is a smoothing or filtering in this demo, just so you can see, but we do provide the raw unfiltered data as well as the raw image of the eye through our API. Excuse me. We can then take this data, display any presentation on the screen, and generate areas of interest, time to first fixation, analyze the fixation in a heat map or gaze plot, analyze emotion as well, and synchronize all that, all the other sensors in the AcqKnowledge program. Just to give you an idea of tips and tricks, when you're positioning an eye tracking sensor, our VT3 Mini, or the Ion tablet, it is important to position the user about an arm's length away. The head box size is, on the Ion, twice as large as our current VT3 Mini, so 40 centimeters to 80 centimeters, you can position them in front of the device, calibrate, and go. We have done a lot of research with government or commercial institutions. Here's a few examples just to kind of walk you through how we have worked in the past with partners synchronizing multiple data streams into one. This is an example we did with Homeland Security through one of our partners, where they connected EEG with eye tracking. And this gives a deeper insight. Actually, in the commercial setting where TSA employees, the baggage screeners in particular, are being trained using our eye trackers on a 2-screen setup. we do have that unique IP to be able to do that. So they calibrate each screen separately, and then we can track both the side view and the top view of the bag as they go through a 20-minute simulation and training exercise. And here's just a short demo of it in action.
ScreenAdapt provides a personalized path to visual search expertise. Develop core visual search skills faster through an individualized training path that addresses skill deficiencies. Immediate feedback that keeps the trainee aware of their progress and errors. Dynamically created combinations of threat and bag images that keeps training fresh and unpredictable. ScreenAdapt uses a personalized training approach based on visual search behavior and performance. Eye tracking makes the visual search process observable to provide immediate feedback. Eye tracking makes it possible to determine the root cause of visual search errors.
So as you can see in this simulation and training exercise, this is very valuable. Their research also tied in EEG, so they could better train these baggage screeners, which is one of the biggest areas of threat in the airport. Another white paper example is the University of Indiana Bloomington was contracted to do a findability study on a product shelf for cereal boxes. In particular, this white paper was identifying how quickly consumers could find the frosted Cheerios on the shelf. You could see in this result here, took 9.4 seconds and a total of 25 fixations. And you can see the gaze plot and how much time they spent on each region, as well as the heat map. So this, you can see, took some time for them to find when you compare it to something a little bit brighter like Apple Jacks, for example. Not a fan of either cereal, but a lot of product package design companies, P&G, a lot of the majors will eye track before they put a new product package design on the shelf. Another use case more on the medical side that we're really excited about is the neuroscience aspect for cognitive impairment and performance analysis. So this is a partnership. We've licensed this application from Mayo Clinic. This was part of a NASA project several years ago where they would baseline screen astronauts before they went up to space to measure the effects of hypoxia, which is the lack of oxygen. Does that truly impact the brain performance? And so they would screen these users using a 27-point test where numbers appear on the screen. There's also a cognitive assessment where they're adding these numbers in sequences of 3. So this is done in 9 times. And I'll show you a demo of this in just a second. But this gives you a fast, quantifiable way to measure brain performance or impairment. And there's current studies going on with Parkinson's and Alzheimer's or MCI patients, both at the VA and Mayo Clinic, about 300 patients currently on each disease to measure and monitor the progression of these horrible diseases. So here's an example of how you set someone up in OCAT. My thinking tool to better understand. So you type in the user's name, you get the user positioned, and then you calibrate the user, and then you walk them through the different numbers. So you'll see the numbers appear randomly. They add those numbers in sequences of 3. And then after those 27 points or 27 numbers appear, there's an actual score that gives the physician or the neurologist or the psychologist quantifiable metrics, gives you data quality, as well as a dashboard of here's the baseline for the diagonal, horizontal, and vertical saccades. There's also a cognitive performance, how quickly did they do the test, analyzes total fixations, blinks as well as pupil size. And then it gives a nice visual scan path where you can see those splotches or the microsaccadic movements of each eye as they stared at those 27 points. And you'll see sometimes some deviations between points. Like here, you can see the scan from one point to the next was very straight, versus here there was a little bit of a deviation. They went up and then over. So when you look at neurological diseases such as Parkinson's and Alzheimer's, you'll see a lot noisier microsaccadic movement, as well as more deviations between points. Last use case that we're eye tracking plus other sensors are really helping is on the education side, especially reading research, to help improve learning outcomes. This you can see in the video is showing a gaze plot of where they were looking on each of the words, and as they stare at a particular target, this circle gets bigger the longer they stare at that. And we're getting to the point with psychologists and other reading experts to be able to using cloud-based solutions through Microsoft Power BI and others to be able to, in real time, diagnose the chances of dyslexia, ADHD, things like that. So you can see here the word, this is all running through Microsoft's immersive reader. The word accessibility was in the red heat map, which means that they spent the longest time reading that particular word. So with that, as you're looking to roll out your research, tying eye tracking with other sensors, it's really important that you get fixed timestamp data that you can correlate brain or heart or skin temperature with eye tracking to better understand in your research. So I hope you can see from the white papers and examples that there's been a lot of research done over the years, and we're here as a partner of BIOPAC to help provide not only a great hardware and software API to provide that, but also a resource as you're building out your studies and solutions. So with that, I'll turn the time back over to Brenda for our first audience poll.
Thanks, Keith. I'll go ahead and launch the poll. Which signals would you like to sync data for, or to? I do have a first couple questions for you, Keith. Are you ready?
Yes.
Would like to know what considerations should be given to environmental conditions when setting up experiments, light levels for pupil data, ensuring consistency, and best research practice with respect to other physiology data collection methods.
Yeah, that's a great question. That's a great question. I can address that. When you're setting up your study, we do tolerate a lot of different lighting conditions with our eye tracker. Because it's infrared, we can track in complete darkness all the way even in bright sunny condition. A big part of our business is actually helping paralyzed people control the computer with their eyes, and with the new Ion tablet, they're mounting these on wheelchairs and using them in tough lighting conditions as well. Because we use a special proprietary strobing technology and notch filter, we can actually filter out a lot of the outside lighting from overwhelming the camera sensor. But when you're setting up your research, you want to make sure you position the system in a location that's consistent. For example, when you position near a window and you do the study in the afternoon and it's really bright sunny day, you will see perhaps smaller pupils because there's more light coming in and constricting the pupil size, versus perhaps it's a cloudy day or you turn the system 180 degrees and you don't get as much light coming into the user's eyes. You will see a little bit of larger pupils in that regard. So you want to keep the location of the device in the exact same position, and also if it's near a window, make note of, was it a bright sunny day or a cloudy day, that you can see some differences, especially in the pupil size constriction when there's more or less light. coming into the user's eyes through a window or in a brighter environment. So my recommendation is, keep it in a location near a wall where the light's going to be the same every time, so you don't have any variability.
Okay, and then Thomas asked, I presume the output includes blink rate and duration?
Yes, so we do output when the eyes are found, both, each eye independently, as well as so you can create your own analytics of that. Excuse me. And we do also output the pupil size in real time for each eye independently.
Okay, thanks. So that's all we have time for right now. I do want to quickly share the results of the poll. 35% people are also tracking EDA, 44% EMG or facial EMG, 12% respiration, 50% ECG, and 38% EOG. And of course, we realize those aren't all of the signals, but those are the main ones that people use for eye tracking. So thank you all for participating. Keep the questions coming. We'll ask more at the break or at the end. Frazer, you're up. I'm making you presenter.
Okay, thanks, Brenda. Okay, good morning, everyone. Thanks, Keith, for that great presentation. I'm going to pick up from where Keith left off. But before I get started, for those of you that are a little unfamiliar with BIOPAC, I want to provide some background information. BIOPAC develops high-quality scientific tools that allow you to measure physiology anytime, anywhere, with any subject. We've been in business for 27 years, and 99% of the top 100 universities use BIOPAC products. We've been cited over 35,000 times, and the BIOPAC Student Lab System is ranked #1 for physiology experiments, the Smart Sensor, the B-Alert X10, and also the Mobita 32-channel biopotential system. So it doesn't matter what platform you're running, it's very easy to combine with the eye tracking system. As far as amplifiers are concerned, you can use our wireless bionomatics platform, our C-series tethered amplifiers, and also the new smart amplifiers. And I'm actually using one of the new smart amplifiers today. I'm going to be the subject. And I've got an ECG 100D, the same as what's shown in the image here. So as Keith's already explained, the eye trackers are designed for screen-based applications. These are portable, so they can be used in or outside of the lab. The bars are lightweight, and the second display can be really quite small as well. I'm actually using a Hewlett-Packard portable monitor. It's 14 inches, this one, V14. Very convenient. It stands up on its own little kickstand, and then the eye tracker just is mounted beneath the display. So for those of you that want to go out in the field, you're not necessarily set up in a lab permanently, these types of displays or the tablet solution that Keith mentioned in his presentation really make for a very portable solution. You use a laptop computer with one of these displays, take your Smart Center or MP160, and you've got a very portable system. So in terms of the eye tracking information, you've got different options, left eye, right eye, or the mean of both eyes. You get gaze angle, gaze velocity. There's a couple of fixation algorithms, dispersion or velocity. And we bring all of that data into AcqKnowledge along with the other physiological signals. So on the left-hand side, you get the view of the eye tracking information with any metrics that are coming off, and then on the right side, on this image, you see the physiological data. For those of you that are familiar with our software, it's easy to set up. You're obviously going to have a lot of familiarity with using it, which is going to make life a lot easier for you. You're basically managing everything through one application, and that application is going to be something that you're already familiar with. So setting up channels for ECG is no different than setting up channels for the eye tracker. In terms of what we're displaying, gaze points show what the person is looking at, and we plot the gaze points over the image to show the gaze path. And then that little red circle there is just showing the pathway between the different gaze points. And then the circles along the path represent the fixations. And they're a group of fixations in one area over a period of time. Give you an example, the person looking over the eye there, get a bunch of fixations. So all of this is displayed within the software. You can display just the fixations on their own, just the points. You can do what's called a graduated display. So the oldest fixation is starting to fade away, whereas the most recent is the darkest. Same also applies for the path. So it's very easy when you look at an image to see the natural path that the person took just by looking at the graduation on there. And then within the software, we allow you to create areas of interest. So you can mask different areas that you particularly care about, and as the participant hits those areas, we track different metrics, different things that you'll be able to do, such as starting and stopping a stimulator. We can send out digital I/O information to trigger other devices or provide some kind of auditory feedback. So the areas of interest provide a little bit more information. Then you get the different types of attention maps, luminance, 3D surface, pie chart, gives you a quick visual indication of how much time was spent on any of your areas of interest. So in this case, there were 3 areas of interest that were active during the experiment, and you can see which ones were the most active. Have a scarf plot. This basically provides you with the pathway the user took with regards to the areas of interest, and then we give the time of each dwell time for that area of interest before the eye moved on to another area. And then the string plot is basically the sequence of areas of interest that were hit during the time the image was presented to the participant. So no time associated with this one, just the sequence of areas of interest. Then we provide a nice report that combines the eye tracking metrics with the physiological data, spits it out into Excel, and I'll be going through all of this in much more detail in the software, but this is just to give you a little bit of an overview, heads up. The stimulus presentation part of it is built into AcqKnowledge, so you can present images, control the duration, etc., etc. You can group the stimuli, you can do randomization of delivery, and then event marks are delivered to AcqKnowledge, so they show up with the physiological data, and you can also send triggers out to other devices. Okay, so I'm going to hand you over to Brenda for our second poll of the morning, and then when we come back, we'll start getting into the software.
All right, thanks, Frazer. I'll go ahead and launch that poll. What type of stimulation are you interested in presenting? And then I'm going to go back to one of the questions that I had for Keith. To which extent does the feeling of a participant to be under surveillance influence the recorded data?
Yeah, that's a great question. I can answer that. With the VT3 Mini, because it magnetically connects and there's a USB cable, single USB cable connection to the laptop, some people can feel like, oh, what is that camera doing? So it is a little invasive. That's why one of the reasons why we came out with the Ion. We did a soft launch at CES earlier this year. 170,000 attendees at the biggest conference in the world. And the feedback from a lot of the Fortune 500 companies that came by was they loved that it basically looked like a Surface tablet, but with eye tracking built in to the bottom of the bezel. And it's, a nice thin 18 millimeters thick design with a kickstand. So you basically set up the tablet, run your study and go, and there's not that extra camera and cable coming out like the VT3 Mini. So if that is of concern, I would highly recommend going with the Ion tablet platform because it is very non-invasive, very sleek design, and also has the touch capability and the webcams all built in, so you can do emotion tracking at the same time.
Okay, thank you. So just so everyone knows, the poll results are 66% images, 28% text, 38% web, 47% desktop application, and 53% other. Ooh, I wonder what that other is. All right, back to you, Frazer. Thank you.
Okay, thanks, Brenda. Thanks, everyone. Welcome back. So what I've got up on the screen, this is some data that I actually recorded just before we went live, and I will record other data, but I figured it's helpful to provide you with some familiarization. So on the left-hand side, we've got one of our typical AcqKnowledge files. The top channel red is ECG. The second channel is heart rate. So these were taken from, this is a lead 2 ECG from myself, using one of the ECG 100D smart amplifiers. Then down below, we've got the gaze X, gaze Y, dispersion, and then pupil diameter for left and right eye. So all of this, no matter what physiological data you're combining, it's all part of the same record. Along the top, you can see we've got these little light bulbs. These light bulbs are the events when an image was changed. On the right-hand side, I've enabled the visualization viewer. That is controlled from the MP160 menu. There's this option down here, show visualization viewer, that opens this dialog on the right. This was the image that was presented at this particular moment in time. If I click over here, you can see the little event marker has changed color. It's red and it's saying worm, and this is the name of this particular image that was presented. And this is completely dynamic. So no matter where I click in the physiological data, it will advance the eye tracking stimulus presentation to that particular moment in time. And then I can just click and drag over an area. And actually, if I make this a little larger, you'll get a better view. I can click and drag over an area like so, and we get to see the gaze path. Okay, so very easy. It's very dynamic. It's one of the nice things about this particular setup. Then you have access to any measurements from the physiological data, and you can see precisely what was going on as far as the eye tracking is concerned. From the visualization path here, we've also got things like the attention map. So this is a 3D map. If I come over, actually, this is a fixed one. Let me just go back through each of these. This is the 3D heat map. So if I swing through like so, these are updated in real time. This is the luminance. So So it just gives you sort of a slightly different view, but a good indication of where the person was looking. These are the metrics for the areas of interest. So I've got some areas of interest, and I'll demonstrate how we create these with the different metrics. And again, this is dynamic also. So if I highlight an area, it immediately updates wherever I'm clicking, it will update to that particular image with those metrics. And then if we want to add physiological measurements as well, we can do that by turning those on down below and then sort of highlight an area, and we'll get physiological data as well if I turn those on. So to turn those on, select add, and I can pick heart rate, for example, and now I've got a heart rate channel added, and we can see those measures are updated. This is the pie chart, so we can see the bulk of the time was spent over the spider. 65.8 beats per minute was the average heart rate over that area. There were 9 fixations. The first entry time was about 2 seconds in, and then the total time over that particular area was about 3.4 seconds. This is the scarf plot that I was talking about earlier. So this is the pathway that was taken with the amount of time on each one. We can also put the time in between. So this image was presented for a total of 10 seconds. And now we've got background. So they initially entered via the background. Then they went to the mouth, then to the background, then to the spider, background, so on and so forth. And then we also have the complete pathway of which of the areas of interest were hit in sequence. Okay, so that gives you sort of a quick familiarization. Now I'm going to show you how to set this up. So I'm going to close this out. First thing that we've built in now is this stimulus presentation. So I'm just going to walk through creating a new one. I'm not going to create an entire 2 monitors. Let me move the display over. There we go. So to add an image, I just come in, select add image, add the spider. At the moment, I'm not controlling the sequence, I'm just bringing in some different types of stimuli. Okay, so I've got 3 different ones. I can then control the sequence. So at the moment, I'll start with, we'll have the cross, then the spider, then the cross, then the worm. Okay, and then if we come back into stimuli, if I select the cross, over on the right, we can actually control the duration that is presented for. So this is in milliseconds. So now this cross will appear on the screen for 3 seconds. We can put an event mark in. So the default is to add an event into the AcqKnowledge file. But we could elect to output a digital event via a digital I/O line, or we can do both. Okay, for most of you, you're probably just going to have it set to event. You can control the background color. Obviously, scaling is important. You want to make sure that the image is presented correctly. And you can just go through and make any tweaks to any of yours. This image is going to be presented for 10 seconds. Again, you can control that. So creating the stimulus presentation is actually relatively straightforward. You also have the ability to create groups. So you can have a group of positive, a group of negative, a group of neutral stimuli, and then they can be randomly presented throughout. And then you can mix and match groups within your sequence. So you don't have to do everything manually. Then once you've created your presentation and if you've got your sequence dialed in, you just come over, hit save, and then when you open an AcqKnowledge file, you can assign the stimulus presentation to that file. So when you run the eye tracking, it knows which presentation you're running. And I'll get into that in a moment. Hey, welcome back everybody. So this is the live demo portion of the webinar. I'm going to walk you through setting up the experiment using AcqKnowledge and combining with the eye tracker. So this is just a graph template that has already been created. I'm going to open it up and walk you through the settings. So I've got an ECG smart amplifier connected. I'm recording heart rate from that ECG signal, and that's the first channel here, heart rate. And then I've got the X and Y gaze, the left and right pupil diameter, and then the dispersion being displayed as well. So these channels, these signals will appear in the graph file in real time as we're monitoring my eyes. Then we go to preview eye tracking. Now this dialog box here basically controls the running of the experiment, and you've got stop and start. Play is the green triangle. You can set this up to to calibrate 5, 9, or 16 point. I'm just going to set it to 5 point. I'm using padding, so what that does, when there's an eye blink, I'm electing to pad with the previous data point so I don't get drops in the signal where the camera shuts off, but you can elect to turn that off. By default it's off, but it just makes the data look a little cleaner. If you want to calculate blinks, of course, you definitely need to remove the padding. I'm going to make sure that I've got this configured right. So this is the monitor that's going to be presenting the stimulus presentation. So make sure that I'm running the correct one, because you've got two monitors. I'm running everything off of my laptop, as I mentioned earlier. Now we've got everything set up, we can hit play. And in a moment, we should see a video of my eyes. And this is what the cameras are looking at. They've detected my pupils, and they've put the crosses on there. You can see the two glint points as well. So this all looks good. At this point, I can hit ready. And now we're at the point where we're going to do our 5-point calibration. So I'm just looking at the green dots on the screen. And once we've completed that, we get the markers to show that I was hitting the target. A little bit off here, but I'm going to hit accept. I could redo that. I'm going to hit accept. Now at this point, I will start to see my stimulus presentation. So I put a cross before each of the images. There are some areas of interest in there, so that we should get some values based on where I'm actually looking. Okay, so now we've finished. I'm going to auto scale my data and do a horizontal auto scale. Come in to show the visualization viewer. Let's try and tidy this up a little bit. Okay, so now if I place my cursor on the recording and drag across, we can see precisely what's going on there. So what I'm going to do is make some little adjustments so that we get a slightly better view. Okay, and I'll increase my tail so that we see more data points. Okay, and I'm going to close that out. So now if I drag across, you can track exactly where I was looking. Advance on to another image. Same with this one. Can drag it across. And then last one, we get the text that appeared on the screen. So this is the gaze path. I can do the heat map. We can do the luminance. So I've created areas of interest around the 3 different words, so we get the information there. A little more interesting over here. Put our pie chart up. So you can see most of the time was spent looking at the spider, a little bit on the left eye, a little bit on the right eye. The insect, the left and the right eye. This is the scarf plot. And then this is the string plot. So this is just the sequence that I moved across. And then finally, there are controls for each of these. The one thing I was going to do is if I come over here, we can put some measurements on and we'll add heart rate. Okay, so now we get the heart rate data up as well. That gives you some idea here. Then finally, I get my report. So this is going to open up in Excel. There we go. So you get the information about the report, the date, you get the summary. This is just the cross. This is the insect. So the labels that I gave for each of my areas of interest. If I just open this up a little bit. There we go. So the area of interest coverage, the dwell time, the number of entries, the time of first entry, the minimum dwell time, the maximum dwell time, the mean dwell time, the number of fixations, time of first fixation, total fixations with a standard deviation, and then the heart rate, 69 for most of those. We move on to the cross, to the spider, the cross again, the worm, and then this is the sequence, the dwell sequence for the insect. You can see the pathway that I took. This is essentially the same as the string plot. So all of this information is available the moment the experiment is complete. Close that out. All these visualizations are available right off the top. Once you've created them, you can jump back into any of them. You can expand these out. Obviously, you can make these full path, so you have a much better view of what's going on. If you've got two monitors, you can have the physiological data on one monitor and the eye tracking on the other. So anyway, that gives you a quick demonstration of the eye tracking from setup all the way through to data collection, all the way through the visualization process. Okay, well, thank you very much for attending our webinar.